Okay, good afternoon. This is a presentation on the properties of atoms, which coordinates with Chapter 19 of your textbook. This particular presentation of this chapter will be broken up into three sections. This section will be a little bit longer than the other two because of the continuity of information for section 1. It's just a little bit longer. So stick with me, certainly. And if you need to, just realize that you can certainly pause at each slide, write down what you need to using the guided notes, and you can certainly mute the narration if you don't want to listen to me. If the material makes sense to you, if you've read the chapter, please, by all means, just make it work for you. But I'm just narrating, so there's context. If anyone out there needs it, it is there. Okay, so with your student learning map, you should have a student learning map, and this is what you would be wanting to be writing down. Remember that the unit essential question will be on the chapter test. Even though it's take home, I'm looking for a very good answer to this question once you get to it. Okay, the key learning, 2 points, matters made from atoms, and the difference in atoms create different kinds of matter. So, unit question, how are the properties of elements determined by the composition of its atoms? And the next would be lesson, essential question. So for section 1, here's the atomic structure concept. And the question here is, what is the composition and structure of the atom? Probably you can answer quite a bit of that already, but let's see what details we might be able to add to your conversation. Okay, key vocabulary. You don't need to write this down. This will all be in context when you get to it in the chapter and the sections. Atom, nucleus, proton, neutron, electron, quark, electron cloud. Most of this, except maybe for quark, should be somewhat familiar to you. Okay, so coming out of 8th grade, you would have been identifying names and symbols of common elements from the periodic table. Moving on from there, though, I would like you to be able to identify quarks as subatomic particles, to be able to describe the electron cloud atomic model, and to explain how electrons are arranged in an atom. So these are our objectives for this section. All right, well, here's the periodic table. And notice that I circled a variety of elements. C, carbon, element number 6, 13, Al, aluminum. Over here we have 19K, potassium. Number 20, Ca, calcium. Healthy teeth and bones, calcium. That's calcium. W, number 74, is tungsten. Number 47, Ag, is silver. This comes from the word argentum. That's where the Ag comes from. 79, a real important one, gold. Au comes from the Latin aurum, A-U-R-E-M. And the W, by the way, comes from the German Wolfram, which is their word for what we call tungsten. Tungsten you would find in the old light bulbs that had kind of a piece of metal that would glow. That piece of metal was made out of tungsten. Okay, so the periodic table. The periodic table, of course, we were just looking at as a chart of all the known elements, of which we now have 118 identified elements. So that 7th row, which sometimes is not completed on older periodic tables, is actually now complete, all the way out to element 118, which has its own name and symbol. It's called oganesson, and its element Og. There are 18 columns, and these columns we call groups. There are 7 rows. The rows are called periods. And the word period itself means a pattern, a reoccurring pattern. So something that is periodic, a reoccurring pattern, would be like the phases of the moon. It's a very good example of something that happens every 29 and a third days, 29 and 1/3 days. It's the same phase all over again. So that's periodic. All of the elements are arranged from low to high by atomic number, which is the number of protons that is found in the nucleus of that atom. It's what makes each element, each atom, unique in that, why is gold different from silver? It literally is because of the protons in the nucleus, and that's it. Every other thing that is different about gold and silver is because of the protons in the nucleus. Sorry about that. So anyway, I could name it anything I wanted to as long as it was appropriate, of course. Spencerium, Pennsylvanium, Kaunesquium, I think would be a pretty cool element. We could, CV, right? That would be great. Or Billnyium. How about that one for Bill Nye the Science Guy? Okay, here is just a list of elements and their symbols. A few of these, actually all of these, were on that circled slide, or the slide with the circles on the periodic table. Notice gold, Au, comes from aurum. Potassium, K, comes from calcium. Silver, Ag, comes from argentum. Tungsten, W, comes from wolfram. Whenever you see a symbol, the first letter is always capitalized, and if there are two letters, then the second letter is always lowercase. The number out here is the number you'll find it on the periodic table, which is its atomic number, which is the number of protons in the nucleus. 13 protons in the nucleus makes it aluminum every time. If it's 12 or 14, it's not aluminum. It's something else, but it's not aluminum. 20 protons exactly, calcium. If it's 19 or 21, it's not calcium. That's how important the number of protons are. It makes the element what it is. Amazing. Here is a traditional, very typical diagram of an atom, certainly very two-dimensional for something that is very three-dimensional. The nucleus is always at the center, and then surrounding the nucleus, which would have protons and neutrons, so this has a little bit of color coding going on. Then you would have electrons, which would orbit the nucleus in a variety of layers, which is how electrons actually orbit. Okay, components of atoms. The center of the atom is called the nucleus. In the nucleus, it will contain protons and neutrons. Protons give the identity of the element, and protons do add mass to the atom as well. Now, protons will have a positive electrical charge, and so they bring positive charges into the nucleus. The neutrons have no charge. They have either a neutral or no charge, so neutrons. What they do is they help to hold the nucleus together. And because there is more than one way to stabilize a nucleus with neutrons, the number of neutrons can vary in a nucleus from one aluminum atom to the next aluminum atom. Every aluminum atom would have to have 13 protons, but they wouldn't necessarily have to have the exact same number of neutrons in the nucleus. But the neutrons would be there to stabilize, but they would not necessarily have to match. The protons, if it's aluminum, have to match. Neutrons, they don't have to match. If the neutrons do not match, we call them isotopes. So if one aluminum atom had 14 neutrons and another aluminum atom had 15 neutrons, they would both be aluminum, but they would be isotopes of aluminum, different kinds of aluminum. Now, chemically, physically, it would all be aluminum and we wouldn't be able to tell the difference. But a chemist or a physicist could, and could be able to tell the difference in isotopes. Neutrons also add mass to an atom. All of the mass of the atom is found in the nucleus. The protons are so small that we don't count them for mass. We count them for other things, but not for mass. So you add the protons and the neutrons together, and that's the mass found in the nucleus. Okay, what about the electrons? Well, the electrons orbit the nucleus outside of the nucleus in an area we call the electron cloud, because the electrons would orbit so fast that it would look like this hazy cloud around a central point if we could actually visualize an atom. And so we refer to that area as the electron cloud. Electrons orbit the nucleus in layers inside of this electron cloud, of which there are 7 main layers. It's all about energy. So how much energy does the electron have as it orbits? Well, if it has a little energy, maybe in level 1. If it has a lot of energy, maybe level 3, maybe orbital level 5, maybe even orbital level 7. So the more energy, the farther away from the nucleus, and 7 is the farthest you can get away. 1 is the closest. Anyway, the electron cloud surrounds the nucleus and is many, many, many times larger than the nucleus. I mean, thousands of times larger than the nucleus. Very much like our solar system versus the sun. Thousands of times bigger. That kind of idea. About atomic particles. So here's just a quick snapshot of these particles, right? So protons found in the nucleus have a positive charge, and they are about the same size and same mass as neutrons. Now notice the symbol here, P positive. P with a superscript positive charge and N with a superscript 0 charge are ways that chemists and scientists actually abbreviate proton and neutron. Neutrons have a neutral electrical charge, or you could just say no charge at all. And neutrons are about the same size and mass as protons. Technically, neutrons are slightly larger than protons, but just a little bit. Electrons are tiny compared with protons or neutrons. So electrons are negative, they have a negative electrical charge, and electrons are about 2,000 times smaller than a proton. So at some point you might say, okay, the atom is made up of protons, neutrons, electrons. Are they made up of anything else? Well, electrons are not made of anything else. The electron is small, solid, and that's it. It's not made of anything else. But protons and neutrons are actually made of smaller particles yet. These particles are called quarks. And there are now 6 known types of quarks. They have very kind of common, almost silly names. One is called the up quark, one is called the down quark, one is called the top or the bottom or charm or strange quark. Very unusual names given the science of it, but there were actually reasons why these names were chosen at the time when they were doing the experiments to discover quarks. But right now we just have these 6 silly names. Now, of all of these 6 types of quarks, the up and the down quark are the most stable, and it's the up and down quarks which actually make the protons and the neutrons. It's just a different combination of up and down quarks. Matter of fact, here we go. So quarks, up, down, top, bottom, charmed, and strange, right? A proton is made of 2 up quarks and 1 down quark. And because they have these weird kind of partial charges, partial electrical charges, an up quark has a partial positive 2/3 charge, and a down quark has a negative 1/3 charge. And if you add all this math, if you do the math, it actually comes up to a positive 1. That's where the proton gets its positive 1 charge. Why does the neutron have no charge? Well, it's made of 1 up and 2 downs. And so if you do their partial charges, check the math out. Positive 2/3 plus a negative 1/3 plus a negative 1/3. These all cancel out. Therefore, there is no charge to the neutron, and it's because of this combination. Are there particles made from other than quarks? No. The other 4 quarks are unstable, and they break down and they turn into the stable up and down quarks. So top, bottom, charmed, and strange basically turn into up and down quarks over time, and then the up and down quarks make up normal matter that we are aware of. Finding quarks. How do we find them? Well, we find them in physics experiments using what are called particle accelerators. So basically we accelerate particles to nearly the speed of light, and then we collide them into each other, look at the explosion, and see what comes out of the explosion. Well, if you do it right, turns out you're going to get quarks coming out of some of those explosions, and we found that that's what makes up protons and neutrons, are those types of quarks. This is a visual from probably a drone or a helicopter looking at a particle accelerator. Now the particle accelerator is actually a tunnel that is underground, where here is the main facility, and these huge immense rings are the accelerators themselves. Now this is kind of like a big figure 8. But all of this is underground actually. It's just a tunnel with a big tube with lots of magnets, and basically, just devices in order to collide these particles and then measure what happens. So here is underground inside the tunnel, which you can, if you're allowed to, you can actually go in the tunnel. And then inside of this great big tube are a series of very high-powered magnets that are all electrically controlled and can pull particles along through a magnetic field to make them go faster and faster and faster and faster until they're traveling at almost the speed of light, and then you just ram them into each other. This is the particle accelerator in Switzerland at CERN. And this thing, I believe, has a diameter of 27 kilometers. It's the largest device ever built on Earth, and it's a particle accelerator. What happens in the explosion? Well, this is actually an image from the explosion. The explosion happens right here. This is where the particle collided with something. Out of this, we get this particle, that, and this. And they interact, sometimes doing these kind of curly Q types of pathways. But in any case, physicists who have done this for a long time understand what all of this actually coming out of this one explosion here, all of this debris, all of these particles, and what they actually are based on how they behave coming out of the explosion. Now, this is a very simple explosion. They can become very complex like this. Check this out. This is like art to me. I mean, this is amazing. I find it beautiful. The explosion was down here. What came out of this explosion is everything else up here. So this might be like a silver atom that exploded. You know, the particle collided with something, and all of these particles are coming out of the silver nucleus, and then the protons are breaking down and colliding with something else and spinning out. So whatever this is, there's a lot of stuff inside of there. And physicists study this, and they can determine what the particles are, and if something is acting unusual, maybe they have discovered a new particle, as opposed to something that oh yeah, we see this all the time, this is a blankety blank, hey wait, this is new, then all of a sudden maybe they've discovered a new particle. Okay, let's move on. Okay, models. In science, we use models, very much like you could build a plastic model of a car, like a 1957 Chevy or a battleship or something. Scientists use models as well in order to represent things that are very hard to study. Sometimes the things are too big, like the solar system. Sometimes the things are too small, like an atom. And so we build models, whether it's a physical model, like the battleship model, or maybe it's a model in a computer, maybe it's a paragraph written in a book, maybe it's a description, maybe it's a math formula. Whatever it is, it's basically a model for a scientist to represent something that's very difficult to study. Well, anyway, the closer the model matches the real object, the more we can study and understand the real object itself. Models should always accomplish three goals in science. They should also always represent as accurately as possible whatever you are studying, whether it's a battleship or an atom, doesn't matter. It should accurately represent it. Then the model should somehow explain part of what you're looking at. So the shape of the hull of a battleship tells you maybe why it floats the way it does. The guns would tell you that it's a defense. It's for defensive capabilities. It's offensive capabilities. It's a war machine, right? And so it's going to explain some of that. And then it should allow for predictions to be made about that, you know, so far as maybe the ability for that battleship to float. Maybe with after it's been hit by a torpedo or two, that it can still float based on the hull design or something like that. So anyway, that's what a model should do, and a model can do more than that, but all science models always do at least this. Examples of models. It could be a three-dimensional model, physically built or in a computer. It could literally be just a description. It could be verbal, could be written, whatever. It could be a math formula, like the circumference of a circle equals the diameter multiplied by the value of pi. So circumference equals diameter times pi. Well, that explains circles, and it explains the ratio of circumference to diameter. So that would be a math formula, but it's a model for a circle. So there you go. Could be a picture, could be a diagram, could be a graph, could be a chart, could be a computer image, could be something embedded into a computer program, and that's just a short list of what models can actually be. So the atomic model, of course, because we're talking about atoms, what about the atomic model? Well, the atomic model is an example of this, and it helps us to understand and explain objects like an atom that are too small to be seen. Okay, so the current model of the atom is called the electron cloud model. Basically, it says this. The area around the nucleus where the electrons are likely to be found in orbit is called the electron cloud. This cloud, these orbits, are hundreds of thousands of times larger than the nucleus, the single point that they are trying to orbit. Electrons would orbit so fast that they would be a blur if we were able to see them. Therefore, it would look like a cloud. So that's kind of where that comes from. So anyway, it would look like a hazy cloud around the nucleus. Remember that we talked earlier that electrons can orbit in up to 7 energy levels. Based on energy, 7 levels, 1 being closest to the nucleus, 7 being the farthest away from the nucleus. The farther you are from the nucleus, the more energy you have to resist the pull of the nucleus. Electrons are negative. The nucleus with the protons inside are positive, and so the negative and the positive attract each other, and that's why the electrons orbit the nucleus, because they are attracted to the nucleus. Very much like the planets orbit the sun, not because of attraction of opposite charges, but because of gravity. A different force, but the same idea about being pulled towards something. Now, the orbits are not very specific paths. It's just a region. It's an area where we would find them. Moving on. Here's an image of an electron cloud with, like on the left here, this would be representing the nucleus, however big the nucleus is. And then the electron cloud is just this fuzzy, hazy area out here where we expect electrons to orbit. So we would expect electrons to be out in here somewhere. This is kind of a similar model where there's the nucleus, and if we were to, say, take a picture 1 a second of the electron, and we were able to put all of these pictures over top of each other, then we might see something like this, where each one of these dots would represent the electron every second. And we would see, oh yeah, okay, well, the electron typically spends its time around in this general area. Sometimes it's a little farther out, sometimes it's a little closer, but otherwise it's just generally in this area. So that would be maybe the first energy level. The second energy level might be way out here farther. So anyway, the electron cloud just tells us where the electrons are most likely going to be at in their orbits. Okay, so the electron cloud model is the current atomic model used, and we call it, again, the electron cloud model. Because we cannot determine exact positions of electrons, we rely on models and predictions to determine information about electrons, because they are very hard to measure and very hard to predict. And so we use models to help us with that. The electron cloud model allows us to predict atom behavior with incredible accuracy. Okay, so this actually concludes section 1. So thank you for sticking with me, 22 minutes into it. This, of course, is your student learning map again, and if I flip the slide, here's the last slide. And this will begin section 2. Now, section 2 will actually be a different video, but I just wanted to give you a heads up for your student learning map where we're going. So in section 2, we're going to look at atomic mass. The question here is, how is atomic mass, sometimes called mass number, how is it computed, and how does it relate to isotopes? Thank you. See you in video number 2.